if you've been watching all the videos up until now, then you're at a stage where your differentiation skills should be quite reasonable. So now we're going to look at uses of linear approximation. And the idea behind a linear approximation is that if you have something complicated, let's say you have a function that's really complicated. Now, if you want to evaluate it at, let's say, at this point here, the idea behind a linear approximation is that you draw a straight line, a tangent line, right at the point that you want to evaluate it, and then rather than looking at this complicated function here, you would look at this line here, and the line here is given by y equals mx plus c. A straight line is given by this simple formula here. So the idea behind linear approximation is that you have something complicated, and then you draw a tangent line. So basically you differentiate this function here. That will give you a gradient. And you know it passes through this particular point here. So therefore you should be able to draw a straight line. And then the idea behind it is that rather than looking at this complicated function, we would then look at this simple straight line here. So for example, let's say you're trying to keep track of thousands of asteroids in space, and you're trying to work out if any of them is going to crash into Earth. So let's just say an asteroid is governed by this formula here, this made-up formula. Okay, so let's just pretend it's governed by this formula here. So rather than keeping track of this complicated, don't forget you've got thousands and thousands of asteroids. So rather than keeping track of all of these here, we would then well, looking at this one here, we would turn into a graph. We'll get a graph plotter and do this, and then let's say you want to evaluate it at, let's say, 2.5 years. Okay, so you want to evaluate it at this point here. So rather than considering this complicated graph here, we would differentiate this whole thing here. Then that will then give us a gradient at this point here. So we therefore know the gradient at this point, and we also know the precise coordinates of this point here, because if you put 2.5, let's say you want to evaluate it at 2.5, let's just say 2.5 years, you would put this into here, and then that will give you the y. So we will know the coordinates at this point here would be 2.5 years, comma, and then you put this into here, and then you work the whole thing out. That will give you this thing here, comma, that thing there. Okay, so we know the coordinates at this point here. We know, well, we will then differentiate this. That will then give us the gradient at this point here. So knowing one point on a straight line, and you know the gradient, therefore you should be able to draw a straight line going through here, a tangent line. Okay, so hang on. So you should be able to draw a tangent line going through there. So now if you just zoom in into this point here, let's say we're going to zoom into this point only. Okay, it will look something like this. You see, when you zoom in and just look at this point only here, you see our straight line here, our y equals mx plus c here, y equals mx plus c here, is pretty good well, it's a good approximation to the complicated line here. So rather than using the complicated line here, just for this area here, we would use our y equals mx plus c. So going back to the asteroid scenario here, so rather than keeping track of all of these here, we would just use mx plus c, and then here we would use mx plus c. It's much simpler when you had to keep track of thousands of things. Okay, so the idea is that we would work out the gradient at a point which we want to evaluate, and then use a straight line to model this complicated thing here. Okay,